All right, folks, let's go ahead and get started. I just want to remind you that after the video is done, please make sure then that you take a picture of the work that you'll be doing during the video. So during the course of the video, I will be stopping to give you time to work on certain problems that I'm going to ask you to do. So you'll do the problems on a separate sheet of paper. So please make sure you remember that. Do the problems on a separate sheet of paper, and then what you'll do then is you'll take a picture of the work and then you'll submit it on Google Classroom. Okay. So let me go ahead. Actually, let me start the timer so that I stay on track here, folks. So please make sure you do that. So at the end of the video, make sure to get in order to get full credit for watching the video. You will also need to submit your work that you will do and submit it to Google Classroom. Okay, so submit it to the same place that you'll find this video in Classroom. Okay. All right. So let's go ahead and let's get started. What I'd like to do today then is I'd like to go ahead and try to finish up we will finish up with the discussion of electron configurations, and then I would like to get started with the discussion of the periodic trends. Not always then we can try to finish up with this chapter, hopefully by the beginning of next week. And so I'll be making an announcement, hopefully on Friday, if not earlier, hopefully tomorrow or on Friday, about the first exam for chapter 6 and when you can expect that. Okay, let's go ahead then and let's take a look at, let me share my screen with you here. And let's take a look at the electron configurations using the periodic table to obtain electron configurations and how we did that yesterday. So let's practice this. I know that not all of the periods finished this problem here, but I want to go ahead and start with this problem for those for the periods that did finish this problem. This will be a review for you. For those who did not finish it, then we'll go ahead and we'll get a chance to finish this problem here. Okay, so let's go ahead and let's take a look at these three elements here, and they were asked to find then the electron configuration. We're going to use the noble gas configuration here, not the expanded notation, but the noble gas configuration here for these elements. So what we want to do then, remember, is we want to make sure we identify what square each one of these elements are located in, which square, where these electrons are located on the periodic table. And then we're going to count. We're going to count squares, very much like what we did when we learned how to write electron configurations using the periodic table. However, what we do here then is if we use the noble gas configuration, we just identify the noble gas that directly precedes the element itself, and then we start our count at the square the square right after that noble gas. So let's go ahead and let's take a look at an example here. Let's do carbon here. So carbon is element number 6. So we see that, so it's element number 6, which means that it occupies the 6th square on the periodic table. Now I'm going to include a few other pieces of information here to help us out here. Okay, so this is the 6th square. Carbon occupies it's in period 2. Okay, so it's in period 2. And this is going to be important later on as we get to bismuth. Okay, so it's in period 2, okay, and the noble gas that precedes it then is going to be helium. So if carbon is element number 6, the noble gas that precedes it then is going to be helium, and so helium then is what we'll put in brackets. So let's go ahead and start with that. Okay, so we're going to say then that helium, and so remember with the noble gas configuration, we put within the brackets the noble gas, and remember noble gases are all located in group 8A, the very last column on the right hand side of the periodic table. And so helium then is the noble gas that precedes it because helium occupies square number 2. Okay. Now with that said, then make sure you understand that this also represents the atomic number for helium, which also represents then that the 2 electrons that helium has. What we're saying here then is that 2 of the 6 electrons that carbon has shares the exact same electron configuration of the location as the 2 electrons here from helium. Okay, which means then that there are 2 electrons that carbon has that are in the 1s orbital. So we don't write that down. Remember, these 2 electrons for helium is in the 1s orbital. So because those 2 electrons are in the same place as these 2 electrons here from helium, we don't need to write that down. Okay, so what we write down is what the remaining 4. We indicate where the remaining 4 electrons are located, and how we do that is then we start our count. If helium is square number 2, okay, we're going to start our count at square number 3. Okay, I'm sorry, square number 3, which represents then the lithium square, and that is in the 2s block. Okay, so second period S block, and so we're going to count that squares. That's the very first square we count, and so we're going to count that square. We're going to count square number 2, 3, square number 4, and so those two squares represent the 2S block, 2S squares. So we indicate that, and then we get to the 2P, and we're going to count 2 squares in to get to carbon. So that represents then the noble gas electron configuration for carbon. And you're going to notice then that if we add these two together, so there it is, those are the 4 electrons that are different. Okay, so we have 4 electrons that are different from helium here. If we add those together, we should get the total number of electrons for carbon as represented by its atomic number right here. Okay, all right. Let's go ahead then. Let's take a look at indium. Indium is the 49th square. It's the 49th element. Okay, so it occupies the 49th square. It is in period. Let me see here. It is in period 5. It's in period 5. Okay. And the noble gas that precedes indium, that comes before indium, then is going to be krypton. Okay. So krypton, then we're going to put that in brackets. Okay. And so krypton then occupies square number 36. It's the 36th element, which means that it has 36 electrons. Again, what that means then is 36 of the 49 of indium's electrons there are identical to that of krypton. Okay? So that means that we don't have to write down the position of these first 36 electrons for indium, at least. For 36 electrons for indium, we don't have to write that down. We already have it here. So we're going to write down the remaining electrons that are different. And so with that said, then if krypton is the 36 square, we're going to start counting at the 37th square, which is where rubidium sits, and that is the 37th square is in the 5s. It's the 5s1 square. We're going to count both 37 and 38 on our way to indium. And we're going to count both of those. That would be 5s2. Then when we get to the 39th square with yttrium, that is going to be in the 4d block. Okay, and we got to count all 10 of those squares on our way to the 49th square right here. Okay, all right, so at the end of that, then the 49th square is indium. That 49th square is in the 5p block, and we only have to count that one square, and we get indium. And so that represents the electron configuration for indium. And again, if you add up all the electrons here, so we have our 13 electrons that are different than that of krypton here, we end up with our 49 total electrons for indium. Okay, all right, so I'm gonna go ahead and save that one. Let's take a look at bismuth. Okay, and let me clear this up, and let's take a look at how we're gonna account for bismuth. Now, I know that I did go over this with you when we talked about lead, but let's go ahead then and let's work this out again. So bismuth is right here. Okay, so let's go ahead and take a look at this. Okay. Bismuth is the 83rd square, and let's see, and it's right here. Okay, so we got to count until we get to 83. Now, if we use the expanded notation, we'd have to start our count here, way up here at hydrogen. Okay, way up here at hydrogen. However, like I said, now that we've learned the noble gas configuration, we want to use this noble gas right here, which is at square number 54. Okay? And so this noble gas here is xenon. This is the noble gas that precedes the bismuth right here. It precedes bismuth here. So we're going to use that in order to start our electron configuration. Okay, so let's go ahead and write that down. Okay, so we're going to write down xenon here, okay, which means then xenon, which is element number 54, shares its 54 electrons. So the position of the 54 electrons for xenon is going to be identical to 54 electrons for bismuth here. Okay, so bismuth here, we'll have to remember that there are 83 total electrons for bismuth. 54 of those will the position of 54 of those will be exactly the same as xenon. So we don't have to write that down. That's the advantage of noble gas configuration here. So with that said, then we can go ahead then and write down whatever the remaining electrons and how they are different from that of xenon. So if xenon is square number 54, we're going to start our count right here. Now, before we do that, I want to make sure I emphasize for you. Okay, if you notice here, bismuth is in period 6, right? So carbon was in period 2, indium was in period 5. Okay. Bismuth is in period 6, and that's going to be important in just a moment. You're going to see why. So that means that we're going to start our count here. So with that said, let's go ahead and take a look at this. We're going to start our count right here at square number 54, which is in the which is in the 6s block right here. Okay, so we're going to count then those two 6s squares. We're going to count those two. So we're going to count those two, and then we get to this point right here. Okay. Now at this point here, this is where quite a few of you made your mistakes. I want to reemphasize then that at this point here, remember the lanthanide and the actinide series. So period 6. These last two, the two bottom rows here, they fit right here in period 6 and period 7. They squeeze in right here. Okay. So what you need to remember to do is once you get to the 55th square here, which is which I'm sorry, the 56th square here. I'm sorry. So this is 55. Sorry. This is 55 right here, you guys. So this is 55, not 54. So this is 55. When we get to the 56th square here, what we need to do is we need to go down and count these elements first. So we're going to count all of these squares here before we get back up here to count the 5D. Okay. So with that said, then what we have to make sure we do then is we got to count those. So that's going to be then, so there's 14 squares here. So this is the 4F. Okay. So we got to count all 14 4F squares here before we start counting right here. And if you look at the numbering, for the from your periodic table, you'll notice then too that these here come before these elements here. Okay. So by the time, so this represents then in your periodic table. Okay, this represents then square number 57 right here. So you got to count square 57 here. Okay, so if you notice then this is 57. You got to drop down and count the 4F. And at the very end here with this square, this is square number 70, and then you go back up here, and this square here is going to be square 71. And so the numbering of the elements here, the numbering of the squares, will remind you that you got to go down here, count this 4F block first before you come back up to start counting the 5D block. Okay, all right. Make sure you keep that in mind. So with that said, we got the 14 4F squares counted. We go back up here. So now we continue our count at square number 71, which is in the 5D. Oops, sorry, 5D. We start continue our count there. So this is going to be then 5D. And we're going to go ahead and we're going to count all 10 of these 5D squares. And so at this point then, we are at square number 81. Okay. And square number 81 is in the 6P block. Okay. And then we're going to count over 3 squares to get to this one. Okay. All right. And so that's how we go about counting the these electrons here. And so if you add up all these electrons here, you will end up getting the total number here. Okay. So make sure you keep that in mind and check. And that's how you will check then if you have the correct electron configuration or not. Okay. All right. So please make sure you make note of that. And if you have any questions on this, come by tomorrow or ask tomorrow, or you can type it in the chat box. You can ask tomorrow about how we got these electron configurations. So once we get down to period 6 and period 7, so the elements for period 6 and period 7, you got to make sure you count the F block elements. Okay, you got to make sure you count those squares in the F block and get that done. Okay. Okay. Very good. Let me go ahead then. So the very first, let's go ahead and do this next problem right here. And so what I'd like you to do is on your paper, let's go ahead and let's practice this here. So on your paper, what I'd like you to do is I want you to write out the electron configuration, and I want you to write out the noble gas electron configuration for these two elements here. So copper and molybdenum, go ahead and find them on your periodic table and take about 2 minutes to write out the electron configuration for these two elements. And then what I'd like you to do is to check your work online. That is, go ahead, once I get you started, pause the video will pause. Go ahead and find, write out what you think the electron configuration will be for these two elements here, and then check your own work. Find it online, find the electron configurations for these two elements online, and then when we meet again, let's take a look at your answers and what you found online. Okay, so take about 2-ish minutes to write out the electron configuration for these elements, and then find the answer online. Okay, go ahead and get that done. Okay, hopefully you were able to write out the electron configuration, and hopefully you were able to find your answer online. And hopefully you're able to see then that there's an oddity, there's something odd about these two elements here. And so let's examine what you found and what we have to do. Okay. All right. So with that said, let's take a look at copper here. So let's go ahead and write down what we know about copper. Okay, so copper is element number 29. So it's the 29th square. So it's element number 29. It's the 29th square. Copper is located in period 4. Okay, so it's in period 4. And the noble gas that precedes copper is going to be argon. Okay, so let's go ahead and let's write this down. So we would put in brackets argon, which is square number, which is element number 18, square number 18. And so we'll start our count then at square number 19, which is going to be potassium, which is in the 4s. Okay, so we're going to have 4s. We're going to count both of the 4s squares there. And then we get to the 3d. Okay, and then we're going to count then over 9 squares to get to copper. Okay, so that is what we expect to be true about copper. So if we follow the Aufbau principle, now remember the principle that we use to obtain the electron configuration here, what we refer to as the Aufbau principle. And we learned about the Aufbau principle back in chapter 5. So the Aufbau principle just tells us in this, that electrons have to fill in the lower energy levels and energy sublevels first before they go on to fill in the higher energy sublevels and levels. Because that's what we have right here. So we expect then 2 electrons to be, we expect in the 4s electrons, 4s orbital to fill in before the 3d orbitals to fill in. And so that's where we get this electron configuration as well. Okay. All right. Doing the same thing. So we followed the Aufbau principle. We did what we were told. Let's go ahead then and let's do the same thing with the with molybdenum. Okay. Molybdenum is element number 42. So this is element number 42. It occupies the 42nd square. It is in period, let me see here, molybdenum, it is in period 5. Okay. And the noble gas that precedes it is going to be krypton. Okay, so let's go ahead then and put krypton in brackets. Okay. And so krypton is element number 36 here. Okay, so it's element number 36. And so we're going to count we're going to start our count at square number 37, which is going to be the 5s. Okay. And we're going to count both of those squares in 5s. Then we get to the 4d, so that'll be 5s2. And then we count then 4d, 1, 2, 3, 4, 4d4 to get to molybdenum. And again, we obtain this electron configuration here by adhering to the Aufbau principle. Okay. All right. So with that said, when you look these up, when you looked up the electron configuration for copper, and when you looked up the electron configuration for molybdenum, I think you might have noticed something strange. No, something strange. So I'm going to go ahead and write down what they actually give you online. Okay, so it's going to be argon, so that's not different. However, the electron configuration then is 4s1 3d10. Okay. For molybdenum, you're going to notice that it's going to be krypton. Okay. 5s1 4d 4d5. Those are the actual electron configurations for these 2 elements here. Now the question then is, it looks like what's happening here is that we've just violated the Aufbau principle. That instead of filling in the lower energy level and sublevels, what these 2 elements have done, that they filled in higher energy levels and sublevels. So the question then is, why is that? Why is it that we have then 2 elements that seem to have violated a principle that we have used to order our electrons? Well, the simple way that we can answer this, though it's not the completely accurate way, but you know we'll work with this for now, is that if you have a partially filled, and this is what we need to make sure that we understand here. If we have a completely filled orbital, now remember with the d orbital there are 5 positions for the electrons to occupy. Okay, 5 shapes for the d. So if you look at the 3d, orbitals here, there are 5 of them. So what these electrons do, remember then, is that they're going to fill it up. So according to Hund's rule, what happens is they're going to fill up, they're going to spread out, okay, first, okay, and then according to the Pauli exclusion principle, then they will flip their spins and they will share that space. Okay, so that's what we have here. If you take a look at what we have here, let's take a look at what we have with the if we follow the off-balance principle. Okay, so if you take a look at these here, so let's go ahead and write in the let's draw out these here. So we have the 1, 2, 3, 4, 5. So let's go ahead and take a look at what happens in this case here. So these are our 3D orbitals. Okay. All right. So it's going to go ahead and we're going to fill it in. So we have then 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. All right. So this is how it would look if the electrons filled the way that we anticipated, we expected them to fill. This is how they actually fill. So what we see here is this, that there is some stability, that if we take a look at what we have here, okay, nature seems to favor then this energy state here, okay, where we have a completely filled d orbital, and it makes copper here more stable. A completely filled d orbital provides the atom, the element, with stability. And this is why stability, I hope I spelled that right. This is why copper doesn't react very well. I mean, you can get copper to oxidize, we see that, but copper is a fairly stable metal. It doesn't change very easily. And that's why we use it in plumbing. That's why we use it in electrical wire. Copper doesn't react very much. And the reason why copper doesn't react very much is because it is stable. And on the subatomic level, the reason why it is stable is because we have this here, a completely filled d orbital that provides the stability that copper has. Okay, all right. So this incomplete. So here we have an incomplete d orbital because we're missing one electron here, and that is not quite as stable. Okay? So what we notice here then is that a general rule that we can rely on is that the more stable an element is going to be, it's going to come down to the stability of its electrons, or how the electrons are configured. Okay? And this is one way that the electrons can be figured and provide then stability for these elements themselves. Okay, so we're going to see that come up again and again. We'll see why, for example, when we get to ions in chapter 7, and how molecular compounds form, how ionic compounds form. We're going to see then that they want to either have completely filled or partially filled orbitals. Okay, all right. And so with that said, then why is it that we have krypton here with this electron configuration? Well, let's go ahead and analyze that as well. Okay, so we're going to look at the 4D. Let's take a look at the 4D orbitals now. So we have 1, 2, 3, 4, 5. So this time we are analyzing, we're looking at the 4D. So this would be the 4D electrons here. And if you notice, then what we have here now is that these electrons will spread out. So we have then 1, 2, 3, 4, 5. Okay. So what we notice here as compared to what we have over here. So let's go ahead and take a look at those electrons. Okay. So we have then 1, 2, 3, 4, 5. Okay, so there are the 4 d orbitals here again. So in this situation here, what we see then is in the d orbitals we have 1, 2, 3, 4. Okay, all right. Now, if an atom can get completely filled d orbitals, it will strive to, but it has to have enough electrons to do so. An alternative way in order to obtain a stability, okay, is that we have here half filled. Okay, so we have a half filled d orbital. We also obtain a certain level of stability. So we have then either a completely filled d orbital or a half filled d orbital. In both cases, then we get stability. We get a more stable atom as opposed to a partially filled d orbital here. And so what both of these atoms seem to do is that they seem to violate the off-balance principle by promoting, and I hesitate to use that word because it's, it's not like copper takes and takes an electron here and it puts it into d orbital. But what we see nature do then is that nature favors this electron configuration where it violates this principle that we have stated, and see them that we, in order to have stability, we have a completely filled or a half filled d orbital as well. Okay, so that's what you want to make sure you keep in mind then as we go through and we start our discussion of how compounds form, starting with ionic compounds in chapter 7. So this is why I like to cover this here, to talk about this, because here we see, first of all, that we have an exception to a rule that we learned, okay? But furthermore, then we have an explanation for it. We have a basis for why this rule that does work most of the time, it works most of the time for every other element, it seems to be violated here with these two elements as we talked about. Now, there are other exceptions as well. There are other exceptions as well. If you take a look at, let's see here, if you take a look at silver, and if you take a look at gold, so the two elements right underneath copper in column 1B, if you take a look at chromium, the element right above molybdenum in column 6B, they are also exceptions. So what you'll need to remember then, and there are many other exceptions, and if you take a look at the inner transition metals, you'll see a lot of exceptions where we violate the off-balance principle, or where the nature violates off-balance principle. But I'm going to ask you this, okay? So you'll need to remember these elements here. Okay, so make sure that you remember that it's going to be chromium, molybdenum, which we just did here, okay? Copper, which we just did here, silver, and gold. Okay, so make sure then that if you ever see any one of these five, so I'm going to ask you to remember this. These are the 5 exceptions that I will ask you to remember. Okay, so these are the 5 exceptions to the off-balance principle. So make sure you can remember these, because if you see them on the exam, if you see them on a quiz, you got to make sure then that you write the electron configuration correctly. You got to remember that these are the 5. So practice these here, write them out, check them. You can check it online like I asked you to do here. Write them out, okay, and then make sure you remember them. Okay, so if you see one of these 5 on the exam, on the quiz, that you remember that they are violate the off-balance principle, and so they will have a completely filled or a half-filled d orbital as a result. So they will promote one of their electrons from the highest s orbital up to the d orbitals here in order to obtain that stability. Okay, so I'm gonna go ahead and save this. So please make sure you keep that in mind as we go through this. Okay, all right. And so with that said, then let me go ahead. Let's summarize what we learned here. So with the exceptions to the off-balance principle, you got to make sure then that the the reason why we have that is that they were trying to obtain either a half-filled, and you got to make sure you keep this in mind, either a half-filled or a completely filled, so half-filled or completely filled d orbital, and that provides more stability for the atom itself. And that's what we got to make, if we can. Now, typically, we will not see more than one electron being promoted. So you'll be tempted to think then that why don't other elements, okay, promote more electrons to obtain this half-filled or completely filled d orbital? Okay, because there is a balance that has to take place between moving an electron up to a d orbital. That takes energy. Remember, we're moving it further away from the nucleus. So there has to be a balance between providing this stability and inputting more energy to promote an electron from a lower energy state up to a higher one. So not all elements will do this. That's why the off-balance principle works. So that's why I said then that there are only a few. There's only a few exceptions. Like I said, there's 5 that you should probably that I would like you to remember for this classroom. There are others. There's more than the 5 that I asked you to point out, but they're not as many. That's why the off-balance principle works, and that's why I taught you the off-balance. That's why we learned the off-balance principle back in chapter 5, and that's why we continue to apply the off-balance principle. Okay, so make sure you keep that in mind. Okay. All right. And so with that said, then what you want to make sure then is that when this does happen, it requires energy. So when electrons are moved into the d orbitals, to obtain this, energy is required. Okay, so there's an energy give and take that has to be considered here when we talk about the movement of electrons from lower energy state the higher energy state. So make sure you keep in mind then that there has to be a balance, and make sure you keep this in mind about energy input, energy input in order for this to happen. And so therefore then that stability comes at the cost of having more energy. Okay, so requirement of more energy. Okay, all right. So with that said, then let's go ahead and let me ask you to, let's take a look at number 12 here. Take a look at number 12, and I would like you to write out the electron configurations for these 4 elements here. Okay, write out the electron configuration for these 4 elements. Don't worry about the extended form. Don't worry about the extended notation. Just go ahead on your paper, write out the electron configuration, the noble gas configuration for these 4 elements. And then when we get back, I'll go over it with you, and then we'll continue on. Okay, so go ahead, write out the electron configuration for these 4. I'll see you back in about 2-ish minutes. Okay, go ahead and get started. Okay, let's go ahead. Let's take a look at this then really quickly. We did bismuth already, so I'm going to go ahead and I'm going to leave it up to you. We did bismuth. Take a look at your notes, okay? And this is element number 83. The only thing I would ask you to do is make sure then you count those f orbitals, okay? All right, let's take a look at polonium here, and I'm going to go ahead then, and to give myself a little bit more room, I'm going to go ahead and open up my whiteboard here really quickly, and then we'll go ahead and we'll consider electron configurations for these 4 elements here. Okay, all right, so let's go ahead then. Polonium is next on the list. Okay, let's take a look at polonium. Okay. All right, so polonium then is element number 84. It occupies the 84th square. Hopefully you'll notice that if you remember bismuth and how we did this, you'll remember this as well. So the noble gas that comes before polonium is going to be xenon. Okay? And so therefore we're going to start our count then at square number 55, which is cesium, in 6s. So we're going to count the first 2 electrons in the 6s period. Remember, we're going to drop down to the 4f. Got to count all 14 of those. Then we get back up to the 5d. We're going to count all 10 of those. And then once we get to 6p, we're going to count 4 electrons, 4 squares to get to polonium. And there it is. That is electron configuration for polonium. Okay, so please make sure if you weren't able to get this on your paper, you check and see what happened. And if you're still not quite sure how you got this, how we got this, please make sure you ask in class tomorrow. Again, just type it into the chat box, guys. At the very beginning of class, type it in the chat box, and then get your questions answered. Okay. Okay, let's take a look at the iodine. Okay. Iodine is element number 53, so it's a 53rd square. Okay. So the noble gas that precedes iodine that comes before is going to be then krypton, which is element number 36. So we'll put that in brackets. So we'll start, and so we'll start our count at square number 37, which is going to be then the 5s. We're going to count both of those, and then we get to the 4d. We count all 10 of those, and then we get to 5p, and we're going to count then 5 squares in order to get to iodine. Now remember, let me just pause here to point out for you then that when we talk about valence electrons, which we will do in just a moment, these are the valence electrons right here for iodine. Even though we have then these 10 electrons here, remember valence electrons deal with the highest energy level. So therefore iodine, very much like all of the other halogens, will have then 7 valence electrons. Okay, so make sure you keep that in mind. We'll talk about that in just a moment. Okay, so remember, it is the highest energy electrons. So the same thing holds true here for polonium. And just to go back really quickly, these are the valence electrons for polonium, and you have 6 of those. And you take a look at that, then they fall 6 valence electrons here, and that corresponds to the group 6a that we find polonium in, and this corresponds to the group 7a that we find iodine in. Okay, so I'll touch on that a little bit more in just a moment. If not, then we'll talk about it tomorrow in class. Okay, all right. With the last one, then let's take a look at tungsten. Tungsten then is going to be element number 74. Okay, okay. It is the 74th square on the periodic table. All right, and so when you write that, so the noble gas that precedes tungsten then is going to be xenon. Okay, so we're going to put xenon in brackets here. and then we're going to go ahead then and we're going to start our count. Okay, so Z9 is element number 50, square number 54. We'll start our count at square number 56, which is going to be 6s. Okay, 6s2, and then we got to count the 4f electrons. Okay, so all 14 of those, so all 14 of those squares, and then we get then 5d4. Okay, so we're going to write that out. And so now with this one here, you would think, well, wait a second. You look at this, you have tungsten, which is element number 74. It's in the same group as chromium and molybdenum. So tungsten is in group 6b. So if you take a look at it, tungsten is in group 6b. So why is it then? And you know, I would encourage you, check online, go ahead and check this electron configuration online and see what you get. And what you get is the exact same electron configuration here. So here we see then not only sorry, hold on one second, you guys. So what we see here then is this is tungsten's electron configuration. So it actually adheres to the off-balance principle. It follows the off-balance principle. It doesn't follow the other two members of its group. So unlike chromium, unlike molybdenum, tungsten does not, we don't see a promotion of this one of these electrons here in order to get a half-filled d orbital here. And that, folks, is the weird, frustrating, but wonderful thing about chemistry. And that is, as soon as you learn about a rule, as soon as you are taught a rule, you are taught then that there are exceptions. And then as soon as you learn about the exceptions, then you're told then that there's another exception to that rule. And so goes science, so goes chemistry. And so that's something that you want to make sure you keep in mind. And that is, you know, for every rule that you were given, there will be exceptions. Okay? And so here we see then that we have an exception to the exception itself. All right. So with that said, then please make sure you guys submit your work online. Don't forget to do that, folks. And what I'll do then is let me go ahead and save this for you. So what we'll do then is tomorrow we will pick up with our discussion here. I want to finish up just quickly analyzing the electron configurations here. In terms of valence electrons, we'll talk about that, and then we'll get started with the periodic trends in the last section of this chapter. Okay. All right. So with that said, then very good, folks. That ends and the first end puzzle video that you're going to watch. And so this is how we'll be doing it from here on out. Okay. Every Wednesday, not every day. Okay. All right. So I will see you folks tomorrow. Have a good rest of your day, and I'll see you tomorrow. Okay. Bye.